Good morning, everyone. Oh, hope you had a good weekend. Monday morning feels like Monday morning to me. We got a lot to do today. We're going to finish up 6.3. I know that I had assigned some problems at the end of class for you to look at. Let me finish up 6.3, and then you should be able to go and attempt to do the rest of that homework. I extended the deadline for it. And then let's see how 6.4 goes, how far we get into it. And then next class, we'll try to get 6.5 in. And then our next exam is in 2 weeks. And we only actually have 4 weeks of class left. And one of those is a test. So we really only have 7 class meetings left, like 7 lectures, I guess you could say. So we're getting to the end here pretty quick. Let's get down to business. So last class, we talked about exponential functions, and I had given you in the beginning of class the law of exponents or laws of exponents. And these were just different properties when we have things raised to powers and how we can combine them together, either multiplying or, if you multiply 2 things that have the same base, you add the exponents. If you raise something to a power and then raise that to a power, you multiply the exponents. And there's, the rest of those properties. So what I'd like to do is I'd like to do some examples here of some problems. These problems are taken out of the physical textbook. And what I'm going to do is just a couple of these. I'm just going to pick some random ones so that hopefully you can get the idea. So what we're doing here is different than what we did at the end of class last time. At the end of class last time, we were graphing exponential functions. So what we're going to do now is we're going to try and solve some equations. And these equations are different than equations we've seen in the past. And you'll recognize that as I start to do these. So let me look at number 66 first. So we have 5 raised to the x equals 5 raised to the negative 6. Okay, so this problem is not difficult. We don't want to make this more complicated than it has to be. We're saying we're trying to figure out what x is, and notice where the position of x. X is up in the exponent of the equation. Normally, equations that we've solved in the past, the x has been down in the base. In other words, like things that we've solved in the past are like this: 3x minus 1 equals 10. That's a linear equation. We've solved things like x squared plus x minus 4 equals 0. That's quadratic, right? We've done polynomials as well. Okay. The x here is appearing in the exponent, right? On all these other ones, the x is down in the base. So this is our first kind of glimpse into how to solve these. Next class, that's all we're going to do is solve exponential and log equations. So this is kind of like an introduction to it. So on this problem, we're saying, okay, 5 raised to what power equals 5 raised to the negative 6 power? Well, since they both have the same exact base, 5, we would need, in order to have for this to be equal, we would need these exponents to be equal to one another. So all we need is for x to be equal to negative 6. And that's it, we're done. There's nothing, like, I guess, challenging in this problem. Now, compare that to number 68. So we have 3 to the negative x equals 81. Now, this is different because we do not have the same base, right? We have 3 here and we have 81 on the other side. Here we have the same base, 5 and 5, so we just set the exponents equal to one another. Here we can't do that. So what I have to recognize, what I have to see here and notice is that the right side of this equation is a power of 3. That's 3 to the 4th power, right? 3 times 3 times 3 times 3, right? 3 to the 4th power is 81. And then if I recognize that, Then I have the same base. And so all I have to do is set the exponents equal to one another. So I just put negative x equals 4, and then divide both sides by -1, you get x is -4. Do y'all see the difference between those two? Right? You have to recognize that 81 is 3 to the 4th power, though. Questions? Let's do 70. 1/4 to the x equals 1/64. So 1/4 to the x equals 1/64. So again, the base on the left-hand side is 1/4. We're trying to solve for x. So what we need to do is see if we can somehow rewrite 1/64 as 1/4 to a power. So what power do I have to raise this to in order to get 1/64? So 1/4 raised to what power gives you the 1/64? What do y'all think? If I take 1/4 and I multiply it times itself, right, twice like that, I get 1/16. That's not it. If I do 1/4 times 1/4 times 1/4, well, that gives me ones across the top, and then on the bottom 4 times 4 times 4, that's 64. So that means that I have to raise this to the 3rd power, which means I have to rewrite this, or I have to basically have x be equal to 3 for this to be true. It's making sense? These are going to get a little more challenging. Let's just keep going here. So let me grab these and take them to the next page. Let's do number 72. That's a good one. So 72, we have 5 raised to the x plus 3 equals 1/5. Okay, the base on the left is 5. And on the right, I have 1/5, right? 1/5. So there's some, what I need is the right-hand side to be 5 to a power, right? 5 to something on the right-hand side. So I'm going to go back again to last class. Remember this property that if you have something to a negative exponent, right, that you can drop it down. That's what it means, right? So if I have something on the bottom, I can move it up. I just have to change the exponent. So let me see. If I take this 1/5, 1/5 is the same as writing 5 to what power? So there's a 1 on this 5, right? So if I bring that up, it'll be 5 to the what? Anyone? Are y'all seeing it or no? -1, right? 5 to the -1 is the same as 1/5. Because if I gave you 5 to the -1, you drop it down as a 1/5, right? So I have to see that. I can rewrite the right-hand side as 5 to the -1. Now they have the same base. And so what I need to do is set this equal to that. So I need x plus 3 to equal -1 in order for this to be true. And then I can subtract 3 on both sides, and I get x must be -4. All right, that seemed to cause a little issue. Are y'all all right with that? Yeah. How about number 74? What if we have 4 to the x squared equals 2 to the x? We've got x's on both sides, don't we? Right? We have x's on both sides. This is different. So one of the bases I have is a 4. The other base I have is a 2, right? So I need to somehow have these have the same base. So what base do you think I should be going for? A 4 or the 2? What do you think? Can I rewrite this 4 as a power of 2, or is it easier to write the 2 as a power of 4? You know what I'm saying or no? What's easier?
The 2.
How do you mean?
I think the 2 is easier because you could just put it to, what is it, like a power of 2?
You can take this, you can take the 4 and rewrite it as 2 squared, right?
Yes.
Yeah, okay, that's what I thought you meant. Okay, so I'm going to take this 4 and I'm going to rewrite that as 2 squared, right? Everyone agree that's 4? But that's being raised to the x squared still, and that equals 2 to the x. Do y'all follow? Just rewrote the 4 as 2 squared. Now, we have the 2 to the power 2 to the power x squared. I can put those together if I somehow combine these powers. What do? Do I add them, multiply them, divide them? Well, again, we go back to this property right here, that if you have something to a power and then all of that to another power, you multiply the 2 powers together, right? So I can rewrite this left side as 2 to the 2x squared. All I did there was multiplied, right? Multiplied 2 times x squared. So I get 2x squared. Now I have the same base, 2, 2. So I can't talk today. What I need to do is set that equal to that. So I just need to set 2x squared equal to x. And we've been through this type of equation before. Be really careful here. Do not divide both sides by x. You're trying to solve this equation, right? Do not divide both sides by x. Bring all your x's to one side. So I'll subtract x on both sides, which gives me 0 on the right. And then I will factor a GCF out. And then I will set each of these factors equal to 0. And I get 2 solutions, 0. And then here I could add 1 to both sides and divide by 2. I have 2 answers. That's the first time this has happened, right? Up to this point, all the answers we've gotten have just been a single answer. Here we have 2 of them. Can I run through any of that again? Is there something that's confusing about that? All right. So the goal is to try and get both sides of the equation to be something to powers, and that base needs to be the same on both sides. If it's the same on both sides, then you can set the exponents equal to one another. The challenge is to get the same base. So we'll do another one. Let's see, that was 74. Let's look at 76. Grab that one real quick. I'll do it right here. Okay, so we have 9 x negative to the negative x plus 15 equals 27 to the x. Okay, thinking about this, we have 2 bases right now, 9 and 27. Be really careful here, because like in this one, we had 2 and 4, and we said, hey, 4 is 2 squared, right? So we could rewrite the 4 as 2 squared. Here, you cannot rewrite the 27 as 9 squared, right? 9 squared is 81. So you cannot rewrite the 27 as a power of 9. And you can't rewrite the 9 as a power of 27 because 27 is bigger than 9. But both of these numbers, 9 and 27, are both powers of what? Henry's saying 3, right? These are both powers of 3. So watch what I'm going to do. This yellow and this green, I'm going to rewrite them. The 9 is really 3 squared, right? But we're still raising that to the negative x plus 15. And that must be equal to the 27, which is 3 cubed, right? 3 times 3 times 3 is 27, but I'm still raising that to the x. So do y'all see? I just rewrote the yellow there. I rewrote the green. Now we're going to do the same thing, the same property. So let me ask someone. I'm going to pick on y'all today. All right. We'll start with the people who don't have their cameras on. So Malak, are you there?
Yes, I'm here.
Okay, thank you. How about the right-hand side of this equation? Can you tell me how I can rewrite this right side using this whole thing that we have something to a power to a power? What do you do with these powers here? Do you know, or
Isn't it the power would have, like, is it something that you would have to add the 3 to the third to get the 27? Is that right?
well, if we do that, we're going to go back to where we were, right? Like if we do 3 to the third, that's where we rewrote the 27 as 3 to the third, right? Because we wanted to get this to have the same base 3 here as this one. I'm saying if we have 3 to the third and then to the x, I can put this 3 and this x together, but how? Do I add them or do I multiply them? So you got to look at these properties here. Do we have this scenario here on the left, or do we have this one on the right?
It's on the right.
Okay, so what did we do? If we have something to a power, what do we do to these two powers, s and t?
Multiply.
Multiply. Okay, so you're going to multiply 3 times x, right? Which is
Yes.
just 3x. So the right-hand side becomes 3 raised to the 3x. Is that all right, Milan?
Yes.
Okay, good. Now, Sana, you've got the left-hand side.
Okay, so can you hear me?
Yes, I can.
Okay, so do we also multiply
Yes.
the powers?
Mm-hmm.
Okay, so would it be, hold on,
Do it on-
negative 2x
Yep, negative 2x. Keep going.
plus 30.
Plus 30, very good. Okay, so everyone, you see what happened here? We're multiplying 2 times the negative x plus 15, right? That's what we're doing. We're going to multiply those two powers together. So the 2 has to distribute through to both of them. The 2 has to hit both. And that's where we get the negative 2x plus 30. Everyone see that? That's a little subtle thing there. Very good. Now that they both have the same base, right? They both have the same base, everyone. So Diego, you there?
Yes, sir.
Okay, what do we do now since they both have the same base?
You set the powers equal to each other.
Set the powers equal to one another. All right, so we set negative 2x plus 30 equal to 3x. And then we solve this, right? We solve this equation. This equation may turn out to be a linear equation, which this one is linear, or it could be like in this problem we did over here, that's quadratic, right? The one that had, let me do something real quick. Pointers, okay. All right, so the one we did over here on the right, we wound up with a quadratic equation, right? Because it had an x squared in it, so we moved everything to one side. Here, this is linear. Okay, we can handle that. I can just add 2x to both sides. And then I get 5x equals 30, divide both sides by 6 or by 5, and you get 6 as an answer. Okay. So we're starting to see that, for these problems, it requires different sorts of thinking, right? For each one. Let me do another one. All right. Which one did we just do? We did 74. We did 76. Let's look at 78. All right. So for 78, 5 to the x squared plus 8 equals 125 to the 2x. All right, Ashley, are you there?
Yes, sir.
Okay, so these don't have the same base, right? 5 and 125.
Mm-hmm.
So can you rewrite one of those as a power of the other one?
Wouldn't be the 125?
Okay, 125 can be rewritten as what? So is 125 a power of 5? So what's 5 squared, right? 5 squared is 25.
Mm-hmm.
And if we multiply that by 5 again, we would get 125, right?
Yes.
Okay, so we can rewrite that as a
It
what?
would be 5. It would be 5 2x.
5 to the third first, right? That's 5 cubed. That's your 125. Yes. With me, Ashley?
Yes.
Okay, and then that to the 2x. Got it?
Is it because we did it 3 times?
Yeah, because the only way you get 125 is if you do 5 times 5 times 5, right?
Mm-hmm.
Okay, so all we're doing is rewriting the 125 as 5 cubed. And now you can use the property. So Ashley, what would I do here with this 3 and this 2x? If I'm taking 5, raising it to the third, raising it to the 2x.
You multiply them?
Okay, and 3 times 2x would give us what?
Isn't it 6x?
Yep, 6x. Okay, good. All right, Zane, we've got the same base. So what do we do now?
You set them equal.
Set the exponents equal, right? So I'm going to set this equal to this. So we've got x squared plus 8 equals 6x. And Zane, what type of equation is that? Linear, quadratic, polynomial, rational?
Quadratic.
Quadratic, right? So we're going to move everything to one side, right? Let's move everything to the left. So we'll have x squared. We'll have a minus 6x when we subtract the 6x on both sides, plus 8 equals 0. And now we have to solve this, right? And we really in this class have like 3 different methods. We could either factor by just kind of guess and check, or we can do quadratic formula, or you can even do synthetic division now because we've learned synthetic division. I'm just going to assume that everyone here could factor this. At somehow, some way, you could figure out this is x minus 4 times x minus 2. So from here to here, the question is, hopefully you can do that, right? And then you set each of those factors equal to 0. So we're going to have 2 answers on this one, 4 and 2. Let me go grab the next problem. I'll come back to that. That's really weird. I don't like that. Okay, so the next problem here, 80, is 9 to the 2x times 27 to the x squared equals 3 to the negative 1. All right, Michael, are you there? Michael G,
Yeah.
are you following this, Michael?
Yes.
Okay, so looking at this, this is different than anything we've done up to this point because we got like a bunch of stuff happening here. The bases we have are 9, 27, and 3. So Michael, do you look at those numbers and look at them like, can you look at them as all being powers of something?
3 powers of 3.
They're all powers of 3. Good. So let's start with the 9. How can you rewrite the 9 here as what?
3 to the second power.
Okay, and then all of that still needs to be raised to what?
2x.
Good. Okay, times. Now, the 27 is what? You said these were all powers of 3. So 27 is 3 what?
3 to the third power.
3 to the third, but then all that still needs to be raised to the
X
square,
to
right?
second power.
Yeah. And then the right side, thank goodness, is 3 to the -1, so we don't have to do anything to that. That's already 3 to a power, right?
Yes.
Okay, good. Raquel, you there?
Uh-huh.
Are you following?
Yes.
Okay, so help me out with these. We got to put this together and this together, right? So what will my next line be?
The first one would be 3 to the 4x.
Okay, good. Times, and then
3 to the 6x. Or x to the 5th, I want to say. Or x to the 6th.
think about what you're doing. You're taking the number 3, right? And you're multiplying it times x squared, right? That's what you're doing?
Oh, yes. So then 3 to the x squared.
3x squared, exactly. So yeah, what you were doing, where you were trying to take the x
I got
squared
kind of
and raise
confused.
to
It
the
looked
third.
like,
Exactly. So just be careful on that, everyone. You're multiplying these, right? Very, very common mistake. So I'm actually glad you did that because we could talk about it. Okay, good. We're here now. All right. Araceli, you there? Lizeth, you there?
Yes, I am.
Okay, good. Are you following, Lizeth?
Yes.
Okay, so this is different than what we've had before, because on all the problems we've had before, we eventually got it to a point where we had like 5 to something equals 5 to something. We just set the exponents equal to one another, right?
Mhm.
On the ones before, we had, let's see, 2 to a power equals 2 to a power, so we set them equal. 5 to a power, 5 to a power, 3 to a power, 3 to a power. We're not there yet, are we? We have 3 to a power times 3 to a power equals 3 to a power. So we need to have just one on each side. So Lizeth, can we do anything to these two to put them together? And I'm going to go back to the properties here.
Okay.
Okay. And let me just grab these properties. We'll go back to the problem we're working on. I'll try and stick them right here. So when you look at these properties, I know that's kind of small, but try and put this in here. Okay. So when we look at these properties, what we have here is a 3 to a power times, right? 3 to a power. So they both have a 3, right?
Mm-hmm.
They have different powers. So if I want to multiply these together, which of these properties is it?
Could we do the first one?
Yep, the very first one right here.
Mhm.
So you're going to take the 2 powers and do what with them?
So would you be adding them?
Add them, right? And
The
just keep
powers?
the same base, right? Keep the same base that we have. Okay, good. So let's see, Lizeth, you tell me what you think this next line is going to be.
So it would be,
So
Is
keep
it
the
like-
base, right? They both have
Yes.
an A here, so keep that base. So our base is what?
3,
3, okay, so 3, and then raise to the what?
4x
4x.
plus 3x squared.
There you go, perfect. Equals 3 to the -1. Got it? Now we have what we had before. We have 3 and 3, right? So all we have to do is set these 2 powers equal to one another, and then we have to still solve that equation, but now we've gotten to that point. Good. Anybody have any questions? Isabella, you there? No, Isabella? Okay, Jose, you're up then. What's my next line?
Yes, sir. We will set them equal to each other.
Okay, so tell me what to write.
It will be 3. No, I'm sorry. 4x plus 3x squared equals -1.
Okay. What type of equation is that?
Would it be quadratic?
Yeah.
Yeah. Right.
Yeah, so let's move everything to one side, right? I think the easiest thing would be to just add 1 on both sides.
Yes, sir.
Okay, and let's put it in descending order. So let's give me the next line written kind of highest power down. What would I have?
It will be, let's see, 3x squared
Okay,
plus 4x
okay.
-1.
Well,
No,
we add,
equal -1.
okay, but we're gonna move that -1 over, right? So we're gonna
Okay.
add 1 here, add 1 on this side,
I'd say it will be +1
+1, then equals.
equals to 0.
Okay, there we go. So now we've got it to a quadratic equation, right? And so once we got it here, we either factor or we use quadratic formula or we use synthetic division. I'm going to just do the factoring, the quick factoring just by looking. This should be a 3x, this should be an x, this should be +1, +1. That should do it. Remember, you could do this with synthetic or you could get the solutions with quadratic formula. It's kind of depends on you. Set each of these equal to 0. And on the first one, we would get -1/3 because we would subtract 1, then divide by 3. And on the second one, we would subtract 1 and get -1. So we have 2 answers. How y'all feeling about this? You know, just got to practice, right? Okay, let's see. That was number 80. Yeah, let's do this. Why don't you take a minute here? See if you can't do this one on your own. It's not that it's harder. All right, it's just using the same properties. It's just the base here is E, which is different, right? But it may as well be a 5 or a 4 or 3 or something like that. Isabella, I got your text. All right, take a minute, see if you can do this one. And you know what I'll do? Let me go back to the other page. I'm going to put it right here. Stick it right here. And that way you can kind of look at what we've done. Okay, there. There you go. I'm gonna give you a few minutes. Why don't you give on the poll, let me know when you're done. I'll stop when I've got at least like 75% of y'all done. That first one is e to the 4th, all of that raised to the x. It's kind of hard to tell that that's a raise, but this is like, you know, a power up here. Good. Just about half of you are done. All right, does someone want to volunteer their answer to me? Go ahead, Henry.
I got like my final answer.
Yes.
I got two solutions. I got -6 and 2.
-6 and 2. Okay, I think that looks right. So first thing to notice is that this 4 and the x can multiply together. So you get e to the 4x times e to the x squared equals e to the 12. And then using that first property, because these both have e and we're multiplying, very important, it's because we're multiplying, we can add those two powers together and put those on an e. So e raised to the 4x plus x squared equals e to the 12. Now that we have the same base, we can set the exponents equal to one another. We get 4x plus x squared equals 12. This is a quadratic equation, so we move everything over to one side. I'll put it in descending order. That means the highest power of x down. And then that quadratic factors x plus 6, x minus 2. And then you set those both equal to 0 and you get -6 and +2. Very good. Any questions on that? Okay.
You
So-
did it so easy.
What's that?
You made it look so easy.
Well,
I was
once
having
you-
a hard time.
once you practice a little bit, you start to, pick up on it. You'll become more confident with it, right? It
I
just
think the
takes a
E
little
was
time.
confusing me.
The E, yeah, just
Yeah.
treat it like another number, like 5 or 3. Remember, we did talk about E last class, right? That special number. Okay. All right. So what I'd like for you to do, let me ask you, what would y'all rather do? I'm going to do a poll question here. Yes or no on this question. So yes would mean that you would prefer to do the odd problems from here. Just these 10 problems right there. Yes is that. No is you would prefer to do the online homework. So you tell me what you would rather do. Yes means let's just do those 10 problems for homework. No means you'll do the homework problems online. Okay, so we're ready. Yeah, 80% of y'all want to do these. Okay, so either take a screenshot of this or I will upload these notes later on. Right after class, I'll upload these notes where I've been doing that every day. Or you can always go back and watch the video or just take a picture with your phone or whatever. Those problems are the ones that you should do for homework. All right.
The circled ones, right?
Circle the odds, and you can stop at 83.
I have a question. Will you
Yes.
take those in for a grade and we will upload them to you the same way we do for the exams?
No, everyone will just get a 100 on it. I'm giving you what you
Okay.
should practice. This is what you should practice to prepare for the test.
Sounds good. Thank
I
you.
think these problems are better than the ones in the online system.
Sir, can I see the rubric, like the one, the orange?
The formulas,
Yes,
those will be at the notes also, right here, that?
yes.
Okay, there you go. Okay, so here's where we are. We kind of have a general idea of what exponential functions are. We know how to graph them, right? We know that they're one-to-one, right? Which meant that they had inverses. And I told you last time, you know, we're going to talk about the inverses, the inverse of the exponential functions. But we took a detour and we looked at how you solve exponential equations, right? And that's what we've been doing so far today. I want to throw one more problem at you, all right? One more problem. This one right here. How about if we had 4 to the 3x equals 5 to the x? And I ask you to solve that for x. Can anybody tell me what the problem is here? What's the issue that's different? Go ahead, Henry, what's up?
You need a common base. So
Yeah,
you'd have to go up to 20.
well, is 20 a power of 4? It's a multiple of 4, right? It's a multiple of 4, but it's not a power of 4.
That got me confused for a second.
You understand? So like there's 4, the best you could do with 4 is make it a 2 squared, right? But 5 is not a power of 2, right? So you can only do powers of 5, which would be 5, 25, 125, and 4 is not any of those, right? 4 to the different powers, you know, 4 squared is 16, 4 cubed, 64. The problem here is we cannot get a common base, right? We can't. There's nothing we can do. So right now, we can't solve this. We can't solve it. All right, yet. All right, we need to develop the next section. Once we develop the ideas of the next section, we will be able to solve this. We just don't have a way of doing it right now. All right. So even though we've learned what we've learned today, we're still very limited in what we can do. We need to be able to write these things as the same base to do what we did today. And that's too limiting. We need something more powerful, right? So let's get into today, the new section. So we're now going to talk about 6.4 logarithmic functions. All right. And the motivation on this, I want to again express to you, the idea here is that what we studied last class, right? We studied exponential functions. And what we said last class, that an exponential function is any function that looks like a to the x, where a had to be positive and a could not be 1. And we talked about they could look 2 different ways. They could either be exponential growth, where they would look like this, or it could be exponential decay, where it looks like this. The one on the left happens if the a is bigger than 1, and the one on the right happens if the a that we have as the base is between 0 and 1. Does that ring a bell from last class? But what I said was both of these situations that we could have, both of these are one-to-one functions, meaning they pass both the vertical and horizontal line test, which means they must have an inverse, right? And the inverse function undoes what a function does, right? That's the whole idea of an inverse function. If you have, I think I talked about like a car wash, right? If a function is a car wash, the inverse like puts all the dirt back on the car, right? It gives you back the dirty car. right? So the question is there an inverse function for an exponential function? Does it exist? We know it does, right? But what is it? Well, that's what logarithmic functions are, all right? They are the inverses of the exponential function. But it's the first time in your life that there's really not an algebraic way to write the function. Like, and I can't stress this enough to you to help you understand that this is going to be confusing. Right now, if I gave you f of x equals, let's go with 2 to the x. We would all agree that that's an exponential function, right? 2 to the x is exponential. The base is 2. This should look like the graph on the left. It should be growth. And if I made a t-table, right? If I made a t-table, plug in x, here's 2 to the x. To graph it, I would plug in -3, -2, -1, 0, 1, 2, 3. That's what I had told everyone we would agree to do. And if you plug these in, you'll get 1, 2, 4, 8, and over here you'll get 1/2, you'll get 1/4, and 1/8. We did this already, so I don't want to go through it too much, right? But the thing I want you to notice is that in order, let's say we wanted to figure out what happens when we plug in 3, right? What we do is we do 2 to the 3rd power, and that gives us 8, right? And that's easy, not easy, but it makes sense algebraically. We're just doing 2 times 2 times 2, right? That's what 2 cubed means, 2 cubed. So the inverse, so think about this, the inverse function, right? The inverse function must do the reverse of this, right? We plug in x. Right now, I don't know what the inverse function is. I'm acting like I don't know what it is, but shouldn't it take 8 and send it back to 3? Take 4, send it back to 2, take 2, send it back to 1, take the 1 back to 0, take the half to -1, take the 1/4 back to -2, and take the 1/8 back to -3. I mean, that's what the inverse should do, right? Take everything back to where it came from. So the question becomes, what is that inverse function, right? Like, what is it? And what I'm telling you is that there is not an easy algebraic way of representing this function. Like 2 to the x means just plug x in and do 2 times itself that many times. There's not going to be something I can give you where I say, oh, plug in 8 and then do this to 8. You're not going to be able to give that to you, okay? It's not going to happen, which is what makes logarithmic functions so confusing, is that they're not really algebraic in the sense that you can't just do this operation that you know how to do, like 2 cubed, that you know how to do. But taking 8 back to 3, there's not something I can tell you to do. Okay, so just, I want you to know that going into this as I now define what a logarithmic function is. If it seems weird, it's because it is weird, all right? So let's go scroll back up and look at what the definition of a logarithmic function is. The logarithmic function of base a, where a is positive and not 1. So it's the same restrictions on a as we had with exponential functions, is denoted y equals, you write the word log, L-O-G, you put a subscript a and then x. And this is read y is logarithm with base a of x. Okay, that's the notation. This is the new notation that we have for the logarithmic function. And then we have this very important statement right here. This right here. This is what we're going to use. Now, I should have put this on a different page. Move this down a little bit. Let me put this right here. Okay, so I want you to let's just read this real quick and then I'll try and explain this. It says here that y is equal to log base a of x if and only if x is equal to a to the y. What? Okay, so let me write this down. I'm going to start with the right side. Do we agree with this? If I wrote 2 cubed, that should be equal to 8. Do y'all see how this kind of matches what's going on the right-hand side here? If you take 2, so if your a is 2 and your y is 3, that should equal to 2 times 2 times 2 should be equal to 8. That is the same as writing this. Okay, so that is the same as you writing this. Okay, so let's write this over here. So what was y for us in this equation? y was the what? The 3, right? So I'm going to write 3 equals log base. Now the a over here was 2. So I put a 2 subscripted here. And the x was the other side, which was 8. So another way I could write that is log base 2 of 8 equals 3. Okay, what I'm highlighting in blue here is the new thing for today, all right? This is the new thing for today. Log base 2 of 8. What is log base 2 of 8? Well, it's equal to 3, right? That's what it says, but why? So imagine that you didn't know this 3 was here, okay? Imagine you didn't know that that was equal to 3, and I asked you, hey, what's log base 2 of 8? What you have to think there is this. You have to be thinking 2 to what power is 8?
The third.
The third, right? But see, then that's not an algebraic operation. That's a mental exercise, isn't it? That's a mental exercise. 2 to what power is 8? Oh, 3, okay? 3. Let me give you another one to see if you're catching on to this. What if I wrote this? Log base 3 of 9. What would that be equal to? So somebody tell me what that's asking. What is it asking me to think? Are y'all not getting it?
Is it asking what exponential like equals to 9, or am I off?
Yeah. It's asking you what you raise 3 to, right? In order to get 9.
Yes,
And what do you raise 3 to get 9?
to the second power.
The second power. So your answer is 2. All right. Let's do another one. Log base 5 of 125. Somebody tell me what the question is that this is asking.
5 to what power is 125?
5 to what power is 125? And can you think of what that is? Careful. 5 raised to what power? So you're saying 5 raised to what power? Let's call it x equals 125. Isn't that what you're asking? And on this one up here, weren't you asking 3 raised to what power is 9?
It's 3.
It should be 3, right? 3. Because we have 5 to the third power is 125. Let's do another one. How about log base 5 of 1/5? Ooh, this one gets people. What's the question it's asking? 5 to what power is what?
1/5.
1/5. What would it be? Who sees it?
Is it -1?
-1. Good. It's -1. Now, how do we know it's -1? You would have to go back to our notes from earlier today. Couldn't we rewrite this other side as 5 to the -1? Like we could have written this as 5 to the x equals 5 to the -1 and then said, oh, x must be -1. I have another one for you. Log base 5 of 1. So what's the question it's asking? 5 to what power is 1, right? That's what it's asking. So what is it? What power do you raise 5 to get 1?
0.
0. Good. So the answer is 0. Are y'all catching on to this? So generally speaking, we have this. If I wrote log base A of x, right? If I wrote that, then what's the question you're asking? Or you know what, let's do it this way. Yeah, I want to match the notes. If I wrote this, right, and asked you, what is that? What is the question you're asking? over here. What's the question you're asking? Come on, y'all can do it.
A to the what power is equal to x?
A to the what power, right? So let's call that power y. We don't know what it is. Isn't that equal to x? Isn't that what you're saying? Think about this. 5 log base 5 of 25 said 5 to what power is 125? Here, log base a of x, we're asking a raised to what power gives me that, right? A raised to what power gives me that? A raised to what power gives me the x? Right? And whatever that answer is, that's what y is. Yeah, that's what y is. This right here is what I was trying to show you. Let me see if I got this right. Right here. Remember this statement right here that I put that's very important? That, does this make a little more sense now? If I write log base a of x, I'm saying a to what power gives me x? That's what this is saying. A to what power gives me x? See, this is an equivalence statement. If you write log base a of x equals y, if you write that down, then what you mean is this. All right? It's weird. It's weird. Okay? It's weird. So because I've been teaching this for so long, I teach my students when it comes to logarithms, I teach them this thing that I call the loop. Okay? This is not going to be in a textbook, all right? But to me, it just makes sense. The loop. Let's say I want to know what log base a of x is. Okay, let's say I want to know what that is, right? That's the question. Well, I say, okay, I'm going to say that that's equal to y. All right. I don't know what it is, but I'm just going to call it y. To understand what's going on here, I use this thing that I'm calling the loop. And here's the loop. I start with a, I raise it to this, and I set that equal to this. Let's just do that over here on the side. If I took a and raised it to the y and set that equal to the x, I would have that relationship that we were talking about a minute ago. Do you see that? This raised to y equals this is the exact relationship that we had before. I'll do a specific example. If we wrote down log base 3 of 27. Now let's do a different one. Let's do 81. Okay, let's say I'm asking you what is that, right? Hey, what is that? Well, let's call this y. All right. And now do the loop. 3 raised to that equals that, right? So I write 3 to the y equals 81. And now we're back to what we were doing before, right? Isn't that back to what we were doing before? I say, oh, okay, well, 3 to the y equals, well, 81 is 3 times 3 times 3 times 3. That's 3 to the 4th power. And now you set these equal to one another, and that means that your answer must be 4. Now, you may not need the loop, okay? You may not need the loop right now, but I promise you later you're going to need it, all right? You're going to need it. So any questions? All right, I want to show you something else before we get to some examples from the book. Yeah. Okay. So when it comes to logarithms, tell me whether or not you believe this is true. I'm going to write something down here. 3 squared equals 9. We all agree with that? 3 squared is 9. But another way I could have written that is log base 3 of 9 equals 2. Those are equivalent statements, aren't they? This first one says 3 squared is 9. And the other one says, hey, 3 to what power is 9? Oh, 2, right? Because if I look at the loop, 3 raised to the 2nd equals 9. Do y'all see that little loop there? 3 raised to that equals 9. So these are equivalent statements, all right? They're equivalent to one another. The one on the left is called the exponential form. And this one is called the logarithmic form. See, both of these are equivalent statements. But one of them is what's called the exponential form of the statement, and the other one is called the logarithmic form of the statement. So let's see if we can do some examples here. These right here. I'm going to put that right. Where was I? Right here. Look at these three statements. We want to take these and change these to what does it say here? Change each exponential statement to an equivalent statement involving a logarithm. So we want to change these from exponential to logarithmic. So let me do the first one. This first one, to convert it to logarithmic, I'm going to write log, okay? And then put equals here. And what I need to come up with is the loop that will create this equation. All right, so I have 1.2 being raised to the third, don't I? 1.2 to the third power. So my base is 1.2. This is a 3, and that's an m. Double check. 1.2 raised to this equals m. Is that equation right there, isn't it? 1.2 raised to the third equals m. So what's in red here is the logarithmic form of the equation above. Try and do B and C on your own. I'm going to give you a minute. I'll do the poll. You can just let me know when you've got the other two done. Notice we're not getting an answer here. We're just rewriting the form. That's all we're doing. We're rewriting in different form. So let me know when you're done with those two. About half of you are done. All right, that's almost all of you. Okay, so on this first one, I need to write that in logarithmic form, so I write log. I put the base here. Well, I know I've got to create the loop to recreate that equation. So the base must be E, and I'm raising the E to B, so B is going to be over here, and then the 9 is going to be there. And then just verify it with the loop. E raised to the B equals 9. Yes, that's the equation we have. Second one, or third one, I should say. I have a log. Here the base is A, right? I'm raising A to the 4th power, so 4 goes here, and then 24 goes there. Make sense? Exponential to logarithmic. The next examples are the other way around. These are easier because you just do the loop and you're done. So here I'm going to take A to the 5th and set it equal to 4. A to the 5th, set it equal to 4. This one, I'm going to take E, raise it to the -3, set it equal to B. here, 3 to the c, and set it equal to 5. Questions? Going from exponential to log, we did. Now we've done log to exponential. Okay, so now let's find the exact values of these. These are logarithmic expressions, right? Let's convert them to exponential. All right, so let's call this, I don't know, let's call that, you can call it anything you want. Let's call it x. Let's call this over here x. And then do the loop. So 2 to the x is 16, right? That's what that's saying. 2 to what power is 16? And what do we raise 2? What do we raise the number 2 to in order to get 16? 2 to what power? 2 times 2 times 2 times. It's 4, right? 4, fourth power. Don't put 8, right? That's 2 times 8 is 16. That's not what we're doing. We're doing 2 raised to a power, right? So this would mean 2 to the 4th is 16, right? So that means your x would have to be 4. See, here we actually found the value of this. So what we're saying at the end of it all is that log base 2 of 16 equals 4. This one, when I create the loop, I'm going to have 3 to what power is 1 over 27. It's a little tricky, but I'll remember that 27 is 3 cubed, right? That's what 27 is. 3 times 3 times 3. And then I can bring that 3 up as a 3 to the negative 3. Right? That 1 over 3 cubed can be brought up as a 3 to the negative 3, and then I can set these two powers equal to one another, so I get x is negative 3. Which means that log base 3 of 1 over 27 equals 3. Oh, sorry, negative 3. Questions on that? So let's go back to where we were earlier. Let me see, right? Where is it? Right here. I'm going to copy this real quick. Okay, earlier we were looking at this. And remember, I was saying, hey, everyone, if I give you 2 to the x, right? If I give you 2 to the x, then it's easy to just go from this table over to these answers, because all you're doing is raising 2 to these powers, which you could do on a calculator or in your head, right? 2 cubed is 8, 2 squared is 4, 2 to the first power is 2. But what about going backwards, right? So look, this is how you go backwards. If I want to know what's happening with 8 and how to get it back to 3, then what I'm going to do is this. I'm going to take log base 2. Now, the reason I'm using base 2 is because look at where it came from, 2 to the x, right? Log base 2 of 8 is what I'm going to do here. Because what does log base 2 of 8 mean? 2 to what power is 8? Well, what's your answer? 2 to what power is 8? 3, right? 3. So that would send you back to 3, wouldn't it? What about this next one? I want to send 4 back to 2. Well, let's try log base 2 of 4. Well, 2 to what power is 4? 2, right? So that sends you back to 2. Let's do the next one. 2 needs to turn into a 1. Well, let's try log base 2 of 2. Well, 2 to what power is 2? 1, right? 2 to the first power. So do you see that this log base 2 is the thing that's sending everything back to where it came from? Do y'all see that? And that's why that logarithmic function is the inverse of this 2 to the x, right? The inverse, right? We were asking, what's the inverse? What's the inverse? Well, the inverse is the log base 2. It's weird, but it's the way it is, all right? Let me see if I'm ready to, yeah, I'm not quite ready to do that yet. Let's do one more thing. I really want to make sure you understand this before I go on. Okay, so let's say we had this original function, f of x equals 4 to the x. That's an exponential function, right? That's an exponential function. The question is, what is its inverse? Right? What is its inverse? Well, we could do our table again, right? We know that this is x, this is 4 to the x. We could go -3, -2, -1, 0, 1, 2, and 3. And then I start plugging in these numbers. And I'll do them quickly because, you know, I'm trying to save us some time here. 4 cubed is 64, 4 squared is 16, 4 to the first power is 4, 4 to the 0 is 1. Then we get 1/4, 1 over 16, and 1 over 64. Okay, those are the numbers we would get if we plugged in -3 through 3. The inverse function has to take those backwards, right? It's got to take that 1 over 64, take it back to -3. It's got to take the 64 and send it back to 3, and then everything in between. So what am I going to use to do that? Well, I've got to use, if this is an exponential function, the inverse is a log function. So I know I'm going to have log here, right? And what is the base of that log going to need to be? What do you think? What is the subscript on that log? Any number we want, or is it somehow connected to this one? What do you think? It's got to be the same as the base here. So it's got to be log base 4, right? Log base 4. And then the things that we're plugging in are these numbers, right? Whatever these numbers are, we need to send those back to somewhere. Let's call those our x values. So we would plug those in right there. This is our inverse function right there. If you're not buying it, try this one right here. I'm going to go log base 4, and then what number am I plugging in? What number am I plugging into this? What's the input of this function? So Henry, you're saying 3. That's what should come out, right? That's what should come out of this function. But what goes into it?
Oh, it's 64.
64,
you're
right?
right.
So if I put 64 here, now you can tell me what that is, because that's saying 4 to what power is 64? And so your answer should be the 3. You see, it sent 64 to 3, just the way I wanted it to. The next one would be 16 has to go back to 2, but I can verify that if I do log base 4 of 16, then of course 4 to what power is 16? Well, that should be 2. So it sent 16 back to 2. So generally speaking, okay, generally speaking, if I give you a function f of x equals a to the x, right? That's an exponential function. Its inverse function should be log what base?
Base A.
Base A. And then the input will be, well, whatever input we want, x. So this is the new thing now, all right? We have this new idea that if somebody gives us an exponential function, we can always find its inverse function, which is just the log function with that same base. And that will take everything back to where it came from. So that's what the next note is about, okay? The next note is basically, well, you know what, that's not what the next note is. Let's, let me see here. Yeah, let's just do, I'm going to define it right here. So a logarithmic function of base A is some function f of x equals log base A of x. The A we have must be bigger than 0, and the A we have cannot be equal to 1. That's what a generic logarithmic function looks like. Now, I didn't put the inverse on it. Do y'all see I didn't put the inverse on it? But that's okay. We know it's the inverse of a to the x. We know it is. But just generally speaking, a logarithmic function is any function that looks like that. Now, let's take a look at the graph of the logarithmic function. All right. And I think I'm going to do Desmos to do this. Let's see here. Now, this is going to go back to a few classes ago when we talked about inverses. So I'm first going to graph 2 to the x. 2 to the x. That's 2 to the x right there. All right. That's what you see there in red. This is no. Geez. This is f of x equals 2 to the x. That is an exponential function, right? That's an exponential function. That's not what I'm talking about. But we know what its inverse looks like, right? And we know what its inverse function is. The inverse of that function is going to be log base 2 of x, right? And we know also that when we graph it, it should be a reflection over the identity, right? When we talked about inverses, we said they have to be reflections over that diagonal line, right? So y'all ready to see it? Let's graph the log base 2 of x. Don't worry about the way I typed it in over here, okay? Just ignore that for right now. That is log base 2 of x right there, all right? There it is, okay? Do y'all agree that that looks like the inverse? Like it does look like a reflection? Okay. I'm gonna change the problem a little bit. Instead of doing 2 to the x, I'm gonna do a to the x. Why is that not graphing that? What the heck? Oh, sorry. Natural log x did the wrong thing. There. Okay. So look, now instead of giving you 2 to the x up here, what I'm giving you is a to the x. Instead of log base 2, I'm giving you log base a. Okay. Now watch what happens when I do a. Right? The bigger a gets, the more rapid the growth is. Look how it changes the log. Okay. See that? Now, do you remember what's going to happen to the red one if I let a get less than 1? We're going to go from growth to decay, right? Watch what happens to the log. Here it goes. Oh, okay. Are they still reflections? They are, right? They are. Let me go back to here. What I'd like for you to think about right now is, let me take a picture of this. Let me place it right here. Oh, that's huge. Oh. Okay, that's basically the graphs that we have. Please carefully pay attention to what I'm about to talk about, all right? I want us to talk about this exponential function first, the red one. What's the domain of this? So that red function, it goes left and right forever, doesn't it? Okay, so the domain is negative infinity to infinity. What about the range of it? Well, it's only from the x-axis up, right? The red one. And it never touches the x-axis. So the range should only go from 0 up forever to infinity, right? That's the red one. The inverse function, the blue one, is different for domain and range. What's the domain of this? Well, it looks like it only exists to the right of the y-axis, right? Only to the right of the y-axis. So it only goes from 0 to infinity. But the range, look at the range. This graph drops down forever, keeps going down, down, down. It has like a vertical asymptote, just drops down. And then to the right, it just keeps growing. It keeps going up and up and up and up and up and up. So it's slowly going up to infinity, but it does keep going. So the range should be from negative infinity to infinity. Do y'all see a similarity between these? They've switched, right? They've switched. So for all logarithmic functions, the domain is 0 to infinity, not including 0. And the range is negative infinity to infinity, which is the opposite of the domain and range for the exponential, which is its inverse. Another way to think about that, if this helps, is that when we're dealing with the function a to the x, which is exponential, we know we can plug in anything into that, but we know that it only spits out numbers between 0 and infinity. And therefore, the inverse function, which goes backwards, this is log base a of x, can only take numbers from 0 to infinity, not including 0. It can only take those numbers back, but it takes it back to everything, negative infinity to infinity. That's another way to visualize the way that domain and range are interconnected. Let me go back to this. Okay, right now, the red one is exponential with a being bigger than 1. This red function is always increasing, right? Increasing. How about the blue one? Increasing or decreasing? Move from left to right. Are you going up or down as you move from left to right? You're going up, right? So it's also increasing. But if I switch it to decay, change my exponential to decay, now it's a decreasing function, right? And so is the logarithmic. It's also decreasing. All right, let me get back to my notes. So here's domain and range of log. I just went through that. Okay. So on this picture, when you don't, please don't lose sight of this. This right here means, are you allowed to plug 0 into a log? Any log, log base 2, log base 3, can you plug 0 in? What's the domain? Everything from 0 to infinity, not including 0, right? So you are never allowed to plug 0 into a log, any log. You also cannot plug in negatives into logs because it has nowhere to send it back, all right? So 0 can't go into a log and negatives can't go into logs. You can only plug positive numbers into logs. And say it again. You can only plug positives into logs. Only positive numbers can go into a log. So let's do this. Find the domain of these logarithmic functions. So these are functions. These are logarithmic functions. The first one is a log base 2. Second one is log base 5. And the last one is log base 1/2. And you're being asked to find the domain. Now, we have to be careful because what I just say, you can only plug positives into logs, right? You can only plug positives into logs. You can't have 0, you can't have a negative, which means when I look at this part A, I need to make sure that x plus 3 is never 0 and never negative, right? Never 0, negative, never negative, which means that the x plus 3 must be bigger than 0, right? Has to be bigger than 0 for this to happen. So just move your 3 to the other side, subtract 3 on both sides. So x must be bigger than -3. On a number line, here's -3. You must be bigger than it. So you do not want to be -3. You want to be everything this way. So that would be from -3 to infinity. That would be your domain. Right? If I try and plug, let's say, what if I try to plug -4 in here? You plug -4 in there, wouldn't you get -1? And I said you cannot plug a negative number into a log. Why can't you plug a negative into a log? Let me just see if I can convince you to make sure you understand it. If I ask you what's log base 2 of -1, right? If I ask you what is that, everyone, then you could say, all right, well, it's equal to x, and then you could do your loop. 2 to the x is -1 is what you'd be asking, right? 2 to what power is -1? Well, guess what? It's never -1. How do we know that? Because when you graph 2 to the x, right, we graphed it earlier. Here's 2 to the x, right? That's the graph of 2 to the x. Is it ever below the x-axis? No. So it's never going to be -1. In fact, it's never going to be 0. It's never going to be any negative number, which is why I have to solve this inequality. Let's do part C. Part C is actually easier than part B. For part C, I need to make sure that the absolute value of x, that must be bigger than 0, right? Has to be positive. I need the absolute value of x to be bigger than 0. Well, wait a minute. Isn't the absolute value of any number going to be positive? Yes. Except what number? What number would cause a problem here?
0.
0, right? Look, I can't plug in 0 into this because what is the absolute value of 0? 0, right? And I can't plug 0 into a log. Now, can I plug in 1? Sure. Absolute value 1 is 1. That's bigger than 0. If I plug in -1, that'll work. I can plug in any number except 0. So I can plug in here 0. I cannot plug in 0, but I can plug anything over here and anything over here. If I do that, that's -infinity to 0. Don't include 0. Union 0 to infinity. So everything except 0 can be plugged in. Let's look at the last one. This one is the trickiest of these. I'm going to move it down here. This will be our last problem for the day. I want to know the domain of this. So first things first, let me write it down. The thing that's in the log, 1 plus x over 1 minus x, we need this to be bigger than 1, don't we? Isn't that what we need? We need that to be bigger than 1. I'm sorry, not bigger than 1. I don't know why I put bigger than 1. I'm being ridiculous. We need it to be bigger than 0. Do y'all agree? Need that to be bigger than 0. Does this look familiar? Does this look familiar? Let me take you back. Let me take you back to March. Let's see here. Here we go, 5.5. Polynomial and rational inequalities. Remember this stuff? This is a rational expression less than 0. We could have done greater than 0. Remember all this method for doing this? I'm about to do that right now. So this would have been on the 23rd of March when we covered this. So what I need to do, and I'm gonna blow through this quickly because we've done it before. I need to see when that's bigger than 0. So what I'm gonna do is I'm gonna think about what the graph of this looks like. If I were to graph that, it's like a rational function. I know that I have an x-intercept at -1. My graph goes through that point. How do I do that? I set the top equal to 0. And then I know that I have a vertical asymptote at 1. Right? How do I know that? I set the bottom equal to 0. Right? And then what I'm going to do is just pick some test points here. Let's say here and here. So I'll go with like -2. I'll go with 0, and I'll go with, that was 1, so I'll go with 2 out here. I'm going to plug these in and check to see if it's true or false. So what happens if I plug -2 into there? So I'm taking -2 and plugging it in here. I get 1 plus -2 over 1 minus -2. Is that bigger than 0? I'm checking. Well, the top is -1. And the bottom is 1 plus 2, so that's a half. Is that true? Is -1/2 bigger than 0? No. So it's not over here. If we plug in 0, I get 1 plus 0 over 1 minus 0. Bigger than 0, is that true? Well, the left side is just 1, and 1 is bigger than 0. That's true. So this region works. And then I try 2 in there. So 1 plus 2 over 1 minus 2, bigger than 0, I'm checking. I get 3 over -1. Wait a minute, that's -3 on the left side. -3 is not bigger than 0, so that doesn't work. So only the numbers between -1 and 1, right? -1 and 1. Do I include -1? Careful. Do I include -1? Was that saying no? Why not? If I plug -1 in here, what do I get? You plug -1 in here for x, what do you get?
0.
0. And can you plug 0 into a log? No. Okay. So I do not want to include -1. Right. And then also when I plug in 1, well, it's undefined. I get division by 0. So my answer is only the stuff between -1 and 1. So the domain of this is -1 to 1, not including the endpoints. Okay. We didn't get through everything here today. I'm going to show you the homework assignment. Let me take a look at this real quick. Yeah. Yeah. Try everything that's highlighted in yellow. Right there. That's your, take a screenshot, take a picture. I'll post these notes later. So you've got the 10 problems from earlier today, along with these. Now, I will just show you that the directions are important here. In the first one, you're going from exponential to log. We did that, like that's using the idea of the loop just to write it from one form to the other. This is changing log to exponent, so you just use the loop. These, you're just using the idea of what a log is. So you're doing like, okay, 2 to what power is 1? Right? 1/5 to what power is 125? And you're supposed to do this without a calculator. See how this goes. This will be interesting to see. You know what? Don't do this, this, or this, because we haven't done those yet. And then the last section is domain, which is what I just covered. So see how these highlighted in yellow go. All right, we'll come back and we'll do more of this next class. You'll have a good rest of your day.
Thank you, Professor. You have a good one.